Dear students, today I am going to discuss Module 4 Digital Signal Processing. The title of the module is Design of IIR Filter, which is the continuation of your third module. In the third module, we have discussed design of IIR filter. Under that, we have discussed Butterworth filter. In this module, we are going to discuss about the Chebyshev filter. Okay, so first let us discuss about the introduction to Chebyshev filter. So here we will see the design of low pass Chebyshev filter, and one more major difference you should know. In the Butterworth filter, in the pass band there is no ripple. In the stop band, ripple will be there. In Chebyshev filter, in the pass band ripples will be there. In the stop band will not be there any ripple. Okay, so that I will show in the next slide. So for designing a Chebyshev IIR digital filter, first we need to design the analog filter, okay, using the given specification. Okay, so the specification will be given in the question. Using that specification, we need to design the analog transfer function. Using that analog transfer function, we need to convert a digital transfer function by using impulse invariant technique or bilinear transformation technique. These are the two techniques we are going to use to convert analog to digital transfer function. Okay, now the analog Chebyshev filter is designed by approximating the ideal frequency response using error function. This error function is nothing but epsilon. It will be denoted by epsilon. Here we are going to discuss two types of approximation. One is type 1 approximation, other one is type 2 approximation. In this, we are in our subject we are going to discuss only type 1 approximation as per the syllabus. Okay, so here now this is the magnitude response of the type 1 Chebyshev low pass filter, which is given by modulus of HA of omega whole square is equal to 1 divided by 1 plus epsilon square Cn square omega divided by omega C. This epsilon is your attenuation constant, and this attenuation constant will be calculated by epsilon equal to 1 by a1 square minus 1 by 2, or epsilon equal to square root of 1 by a1 square minus 1, and this a1 is the gain of the passband frequency. Okay, so gain of the passband frequency, and here this a1 is the gain of the passband frequency, where the cutoff frequency will be omega 1, and the Chebyshev polynomial of the first kind of degree n will be given by, generally it is given by Cn of x is equal to cos open the bracket n cos inverse x for x is less than or equal to 1, and for cos n cos h inverse x for x is greater than or equal to 1. For less than, there will not be hyperbolic. For greater than, there will be the hyperbolic. We are going to use the second equation. And now I have told now, so this is the filter response of your Chebyshev filter, and this you see, this is the pass band frequency, and this is the cutoff frequency, that is stop band frequency, and this is the pass band cutoff frequency, this is the stop band cutoff frequency. As I said earlier, in the pass band you will have ripples. In the stop band, ripple will not be there. As the frequency increases, your gain will be decreasing monotonically, and this is the Chebyshev low pass filter. We know the general characteristics of low pass filter. The filter Chebyshev low pass filter will also be same. Only thing is here your pass band will have some ripples. That's all. And this is your gain of the that is pass band, which is denoted as A1, and this A2 is nothing but your gain of your stop band, and this omega 1 is the cutoff frequency for your pass band frequency gain A1, and omega 2 is the gain of your stop cutoff frequency of your stop band gain. Okay, and this is about your Chebyshev type 1 filter magnitude response. Okay, and now we will discuss some of the design parameters of your low pass Chebyshev filter. and this A1 we know that it is a pass band frequency, and this A2 is your stop band frequency. This will be very important. From the given specification, you need to design the analog transfer function, and this omega 1 is the cutoff frequency of your gain A1, and omega 2 is the cutoff frequency of omega 2 is the cutoff frequency of your gain A2. Okay, and here this gain A1 will be it should be located between your below your magnitude response 1. Okay, and this A1 will be given as A1 square less than or equal to 1 divided by 1 plus epsilon square Cn square omega 1 divided by omega 2, and your the gain will be A2 is nothing but your stop band gain, that should be less than that of um, your this one A1, and this should be this 1 divided by 1 plus epsilon square Cn square omega 1 divided by omega 2. Okay, it should be greater than or equal to this A2. Okay, and here we are going to assume that your cutoff frequency will be is equal to omega 1, and so that this equation value will be is equal to 1. Therefore, from the above, the inequality involving A square, so this A1 square, this is your gain of your passband frequency. A1 square less than or equal to 1 divided by epsilon square. And assuming equality in the equation, in order to find the attenuation factor epsilon will be is equal to 1 divided by A1 square minus 1, that is to the power 1 by 2, or we can say epsilon is equal to square root of 1 by A1 square minus 1. In order, the order of the analog filter we need to calculate. Okay, in order to find the order of the analog filter, and we need to calculate A2 also. Okay, so assuming omega c is equal to omega 1, and if you simplify this equation, the order of the filter will be calculated. N is greater than or equal to cos h inverse of 1 by epsilon square root of 1 by A2 square minus 1 divided by cos h inverse of omega 2 divided by omega 1. This A2 is nothing but your gain of your stop band. Okay, A1 is nothing but your gain of your pass band. Epsilon is the attenuation factor. So this an order of the filter. In order to find the order of the filter, this is very important. This n is greater than or equal to cos h inverse of 1 by epsilon square root of 1 by A2 square minus 1 whole divided by cos h inverse of omega 2 divided by omega 1. So A2 is the gain of the stop band frequency, stop band gain. Okay, so this is very important formula to find the order of the filter. And also one more thing, as the order increases, the gain decreases very fast. Okay, that you should know. So order is very important. We need to calculate. If the order is even, or if the order is odd, then there will be some formula to find the transfer function. Okay, so after finding the order, we need to design the analog transfer function from the given specification. So if the order is odd, then the transfer function for analog transfer function will be given by HA of S is equal to B naught omega C divided by S plus omega C. We know that omega C is the cutoff frequency, where pi of k varies from 1 to n minus 1 divided by 2. This is very important. Here see, it is for order n is odd, then this n will be given as n minus 1 divided by 2 bk omega c square divided by s square plus bk omega c s plus ck omega c. And this finally this analog transfer function will be simplified, and it will be given as HA of S is equal to pi of k equal to 1 to n by 2 bk omega c square divided by s square plus bk omega c s plus ck omega c square. This is the bk coefficient, ck coefficient, and c naught we need to calculate. And now this is a yn formula is 1 by 2, 1 by epsilon square plus 1 square root plus 1 by epsilon whole power 1 by n minus square root of 1 by epsilon square plus 1 plus 1 by epsilon whole power minus 1 by n. If the order of the filter is even, then this HA of S is equal to under S tends to 0, 1 divided by square root of 1 plus epsilon square So this is very important. These are the formulas we are going to design the filters. Thank you.